Hello, it's a great pleasure for me to speak at a conference dedicated to Klaus, my favorite co-author, and I am very grateful to the organizers for the opportunity to give a talk here. Klaus and I share the same mathematical passion. We like to build bridges between algebraic geometry on one side and convex geometry on the other side. In my talk, I will describe a new construction that bridges algebraic and convex geometry, which I call geometric mitosis. The main motivation to build such bridges, of course, comes from toric geometry. And in the toric case, such bridges are quite solid. My construction is more general, so it applies to setting where no group action is present. So in the first part of my talk, I will describe this general construction. And in the second part of my talk, I will apply this construction to geometry of Fleck varieties, because our conference is on group actions in algebraic geometry. My main examples will be examples with nice group actions. And the term mitosis was brought from biology to mathematics about 20 years ago by Alan Knudsen and Ezra Miller. And I will explain how my construction is related to the original mitosis of Knudsen-Miller and various generalizations that were obtained during the last 20 years. For the rest of my talk, I will switch to a digital blackboard, or rather whiteboard. To define mitosis, I don't actually need any background. However, to motivate the definition, I would like to remind you the concept of polytope ring introduced by Askold Khovanskii and Alexander Puklikov. So let P be a convex polytope in Rd, and we assume that it has full dimensions. So P is a d-dimensional polytope in a d-dimensional space. Khovanskii and Puklikov developed a general construction with a convex polytope. They associated a graded commutative ring. And this ring only has components that live in degrees from 0 to d, where d is the dimension of P. The meaning of this ring is that, of course, it is a Kramolge ring or Chow ring of a certain variety. This is not always the case. However, if P is a simple lattice polytope with extra condition so that the corresponding toric variety is smooth, then the Chow ring of this toric variety is indeed isomorphic to the polytope ring. And this was original motivation behind definition of Khovanskii and Puklikov. So from toric geometry, we know that projective toric varieties together with a fixed projective embedding can be labeled by convex polytopes, which are called Newton polytopes. And if we take a Newton polytope corresponding to a very ample line bundle on the toric variety and apply construction of Khovanskii-Puklikov, then we will get the Chow ring of this toric variety. However, the polytope ring can be defined for any polytope, not necessarily simple, And what is interesting is that sometimes it is a Chow-ring of a certain smooth non-toric variety. And this will be the main source of examples today. The case when there is a non-toric variety whose Chow-ring can still be described as a polytope ring of certain non-simple polytope. The definition of polytope ring doesn't use any algebraic geometry, so it's purely convex geometric definition. And because of this, it can be applied in non-toric cases, because we don't really need to think about any underlying toric variety or toric degeneration of a non-toric variety. We can really think only in terms of convex geometry, in terms of polytope and its faces and intersection of faces. So let me give this convex geometric definition. So first, with polytope, we may associate a semi-group of all polytopes with the same normal fan. They are also called polytopes analogous to P. One can think of a polytope analogous to P as follows. So let us move hyperplanes that contain facets of P. And let us move them so that they remain parallel to the original facets. Then we will get a different polytope whose facets are parallel to the facets of P. And if in the process of moving facets we haven't changed combinatorial type of the polytope, then we say that the resulting polytope is still analogous to P. All these polytopes analogous to P form a semigroup with respect to Minkowski sum. A down-to-earth way to think about them is just to define the polytope P by linear inequalities, and then we can choose an equality so that in the left-hand side we have a linear function, and on the right-hand side we have a constant. And then these constants can be thought as parameters. When we change parameters, we get different polytopes analogous to P. So let us consider a simple example, which I will use throughout my talk to illustrate all definitions. So let P be a trapezoid in R2 given by the following equations. So x is between 0 and a, y is greater than 0, and x plus y is less than a plus b. If a and b are some fixed numbers, then this is a single polytope P. And if we start to change a and b, we get a whole family of polytopes analogous to P. Of course, these are not all polytopes analogous to P, because we may also make parallel translations of P, or in other words, we may change coordinates of the lower left vertex of P. So originally the lower left vertex of P is the origin, and if we move origin to x0, y0, then we will get a polytope which is also analogous to P. So the most general form of a polytope analogous to P depends on 4 parameters: a, b, x0, y0. Of course, there are certain positivity conditions on these parameters, because if we just take arbitrary quadruple a, b, x0, y0, we will not get necessarily a convex polytope. We don't actually care about precise positivity conditions. Just remark that we choose a, b, x0, and y0 so that this polytope is indeed analogous to P. And now we complete this semigroup formally to its Grothendieck group. So we take formal differences of polytopes analogous to P. And it's easy to check that SP is cancellation free. So it is indeed a subset of its Grothendieck group. So one way to construct this group is just to take formal differences. Another way to think about this group is just to consider inequalities that define polytopes analogous to P and forget about any positivity conditions on the constants in the right-hand sides. In particular, in the example that we considered, the example with trapezoid, we will now allow A, B, x naught, y naught to take any real values. So at the first glance it seems that we just got four-dimensional vector space, nothing interesting. It is important that this vector space contains a semigroup of polytopes analogous to P, and we will use this. There are more geometric ways to think about virtual polytopes. For instance, one can think of a usual convex polytope as the intersection of half spaces. And here we still have half spaces. In this example, we have 4 half planes. However, their intersection is no longer a polytope, or maybe they don't have a common intersection at all, like in this particular picture. We have a shape which is clearly not a trapezoid. One might assign certain multiplicities to different subsets that we get by intersecting these half spaces. And there is a language for dealing with virtual polytopes in a geometric way. This language was also developed by Khovanskii and Puklikov. Namely, they defined convex chains, which are linear combinations of convex polytopes with possibly negative coefficients. And virtual polytopes are best described as convex chains. So I will now give the definition of Khovanskii-Puklikov ring, or polytope ring. We take the Grothendieck group LP, and in general it is a vector space of dimension L, where L is strictly less than the number of hyperplane faces of P. If P is simple, so at every vertex only D edges meet, then this inequality is exact. So the dimension of LP is exactly the number of facets of P. However, if P is not simple, and this is the most interesting case for me in my talk, then L is strictly less than D, because we cannot move faces independently. If too many faces meet at the same vertex, then we cannot move just one facet, because this certainly change combinatorial type of the polytope. And here I have a typo in my slide. It's written that L is less than or equal to D. Of course, instead of D, I should have written the number of hyperplane facets of P. The definition can be given in a coordinate-free way. However, in main examples that I'm going to consider, there will be a certain natural choice of coordinates. So for simplicity, let me fix some coordinates on LP, x1, so on xl. Then the polytope ring is defined as the ring of polynomials with integer coefficients in L variables, d1, so on dl, where by di I mean the partial derivative with respect to xi. And this ring should be quotiented by the ideal that consists of all differential operators that do annihilate the volume polynomial. And to define the volume polynomial, we actually have to remember that the semigroup SP is sitting inside LP. So LP is not just an abstract L-dimensional vector space, but it contains this intricate semigroup of convex polytopes analogous to P. So the volume polynomial is a function that can be defined on SP just by assigning the volume of a polytope to every polytope Q and SP. Of course, to define the volume, we have to fix certain translation invariant volume form on RD. So let us fix such a form, and then every polytope has a well-defined volume. And so we have a function on SP. This function, this is easy to check, will be a homogeneous polynomial of degree D. And because it's a polynomial, we can extend it as a polynomial to the whole space LP. So a priori, this function is defined only on some semigroup, but because it's a polynomial, there is a natural way to extend it to the whole vector space. And this is how we define volume polynomial. From this definition, it's clear that the polytope ring doesn't contain elements of degree greater than D, because volume polynomial is homogeneous of degree D. So any differential operator, any homogeneous differential operator of degree greater than D will annihilate the volume polynomial. So this is the general definition, and now let us apply it to our example with trapezoid.